Let's take a look at this other optimization problem. This one's kind of tough. It's asking us, says, a 6 foot tall fence runs parallel to the wall of a house at a distance of 7 feet. Find the length of the shortest ladder that extends from the ground to the house without touching the fence. And then we say, assume that the vertical wall of the house is 25 foot high and the horizontal ground extends 25 feet from the fence. Okay, so I went ahead and labeled what I had best I could with a triangle. We know that the ladder is going to lean against the house, and it said that the maximum height up the house it could be is 25. Now, I went ahead and said that the range for the y, or you could think of it as the domain for the y values there, we know a reasonable height for that y. There's no way it could be less than 6 because the ladder's going to have to lean up and go up above that. So I went ahead and said, I know y is some number. It can't be 6, but it could be greater than 6 all the way up to 25. So I said, all right, y is some number between 6 and 25. Now, we were explicitly told that the fence is 7 feet from the wall and then that the fence is 6 feet tall. Okay, now we also know that the base of the ladder can extend. It says assume the vertical wall of the house is 25 foot wall or 25 feet high and the horizontal ground extends 25 feet from the fence. So you have the option of extending the ladder as far out as 25 foot away. Now, of course, that means X could be any number. If it's 0, then you're going to place it right against the fence, and that wouldn't make any sense. So I can say, well, okay, it can't be 0. And if it were 25, you would not be minimizing the length of the fence. You would be maximizing the length of the fence. So we know that X, it has to be some number in between 0 and whatever 25 is out here. So we'll just say, well, X is some number between 0 and 25. Now, we know that the length of the ladder is going to be the hypotenuse of this triangle. So I would just say, well, okay, Pythagorean theorem, it's the square of the base, which is going to be x plus 7 squared, plus the square of the height. Y squared is equal to the square of the length that we're looking for, that I'm calling z squared. Okay, now I can get this into one equation in terms of x by using similar triangles over here. I can say, if you notice, we have two similar triangles. We have the large triangle right here, and then we have a smaller triangle within there, this one. Because both the height of the wall and the height of the fence are assumed to be at right angles. They both share this angle, which means this angle has to be the same as this angle. All equal angles, that means sides are proportional. Thus, I can say the height over the base of the small triangle must equal the height over the base of the large triangle. That's where I got this 6 over x has to equal y over x plus 7. Now, needed to get an equation for y in terms of x. So I can say, well, we can cross multiply. 6 times x plus 7 is going to give me 6 times x plus 6 times 7 is 42. And I get an x times y on the other side. Now, solve for y by dividing both sides by x. When I divide by x, 6x divided by x is 42. And 6x divided by x is 6, and then 42 over x I just leave as 42 over x. Now, that enables me to take this expression in terms of x and place it into my Pythagorean identity in the place of y squared. So I get 6 plus 42 over x quantity squared is replacing y squared in my Pythagorean identity. So I can say that the length that I'm looking for squared is just x plus 7 quantity squared plus this group 6 plus 42 over x squared. I needed to simplify that expression out. So I did here. I said, okay, then z squared is equal to, this is just x plus 7 times x plus 7. This next part is saying 6 plus 42 over x times 6 plus 42 over x. It's squaring that out. Okay, now at that point, I needed to say, well, I got to have some way to minimize this. This is the square of the length. So I'm thinking, well, okay, since I know that the length z has to be positive, I know that its minimum is going to occur at the exact same critical point as where the minimum of z occurs. So I don't have to go through, fortunately, and try to take the square root of this horrendous expression. That would be messy. So I can say instead, the logic I'm going to use here is I can say since z has a minimum where z squared has a minimum, I can find the minimum of z squared. Okay, so what does that mean? It means I can go ahead and take this expression in terms of z, and the only thing I did here is rearrange the terms and write this x in the denominator as x to the negative 1, this x squared in the denominator as x to the negative 2, put my constants at the end. So I have all my terms of x and then my constants. Now, I'm taking that equation that I have here that represents the square of the length that I'm looking for, and I can say, well, the critical point's going to be at where the derivative of this expression is equal to 0. So I say, well, let's take the derivative of this expression. Derivative of x squared is 2x. Derivative of 14x is 14. 504x to the negative 1 becomes negative 504x to the negative 2. 1764x to the negative 2 becomes negative 3528x to the negative 3. I needed to set all of that equal to 0. And I was thinking, okay, that's not something that I can do by hand. So I brought in my calculator and I said, all right, all I have to do is find the x-intercepts of this function. And I know that the x-intercepts have to occur somewhere from 0 to 25, guaranteed. So I put this equation in y1, I put this equation in y2 since I'm trying to set it equal to 0, and I set the window on my calculator between 0 and 25. Some good y values in this case. Now we know that we're interested in y equals 0, so there's no need to go far out on the y's. Negative 10 to 30 gives you a pretty decent graph of this function over this region. And then after you get this one in and this one in and your x values, you really don't need to worry about the y values. You just hit second calc 5, and then you'll hit enter 3 times, and it will give you this value for x. This is the value for x such that the derivative of the square of this lengths equation is equal to 0. So I can say, well, all right, now that's still not answering my question. I need to go back and answer my question. Well, I know that z squared is the group x plus 7 squared plus y squared. So the length that I'm looking for, z, is going to be the square root of my x plus 7 squared. That's just this number plus 7. That's the 13.3163596 squared. And then plus y squared becomes plus this group right here. I'll have 6 plus 42 over the x value that I found, quantity squared. If you plug all of this into your calculator, take the square root of that expression, you get 18.3662. Now, my lab was wanting an answer to 1 decimal place, and so this rounded to 1 decimal place would be 18.4, which, if you notice over here, this is the value my lab was wanting for this question. This is a bit of a tough question. I prefer questions where you can find the critical points manually rather than having to depend upon a graphing calculator. This one would have been tough to find manually, at least in this format. This is not a type of question I would give you on a test, but still a good question for the homework. Hopefully this helps you make some sense out of it.